So I guess we'll just continue like from where we left off. So let's give some example like for the channel Gaussian theorem. So let me just have a new page here. So let's start with the simplest channel we can think of. It's a binary symmetric channel. So it's symmetric instead, and also it's binary. So it means that like the input and output is only 0 and 1. So I have 0, 1 and coming in, 0 and 1 coming out, and it's symmetric that basically if I come in 1, it sometimes will send out 1. Actually, most of the time it will send out 1. So with probability 1 minus p. But also that sometimes you will just get an error that will send out 0 instead. So basically that's what is going on. And p is typically less than 0.5. Yeah. And of course, like the same case is like if the input sending 0 here, because it's symmetric, in the sense like that will be like 1 minus p probability that will send out a 0, and with probability p that will send out a 1. So that's the binary symmetric channel. So very simple setup here. And so, or I can write like something like py given x, and get a 1 given 1. I mean, with an input 0 with output 1 is equal to py given x, with output 0 input 1 is equal to p. And actually, by the way, the p here is known as the crossover probability.
That is the probability 1.
That's the probability that like you're having error basically.
Yeah, having error.
And then like py given x 1 1 is equal to py given x 0 0 is equal to 1 minus p. And then the capacity, as we described earlier, is equal to maximums of ixy over the input pxy, input distribution. Now I can write this as maximum hy minus hy given x, px here. And of course, y given x is fixed, right? So the conditional probability is fixed because this only depends on the, I should say, because this one here is actually equal to summation px h y given small x, right? X equal to small x here. No matter what small x you given in, because it's symmetric, whether x is equal to 1 or 0, x is basically 0 or 1 here. Whether it's 0 or 1, hy given x is still equal to what? Something equal to hp, right? Think of like if I'm sending out 0, then what I'm observing y will be with probability, if x is equal to 0, then y will have a distribution that is equal to 1 with probability p, and 0 with probability 1 minus p, right?
Yeah,
yes. And then if you compute the entropy of that, I will just shorthand notation is hp, right? That's hp is basically is equal to p log p minus p log p minus 1 minus p log p log 1 minus p. And similarly, like for x equal to 1 also, we will have y is equal to 1 and 0 with probability 1 minus p and p. Again, the entropy is still like is equal to hp basically. The hy given x equal to 1 is still equal to hp. So in either case, hy given x equal to 0 or equal to 1 is both equal to hp. So therefore, this does not actually, the average, therefore will not depend on the distribution px here. So therefore, this guy will be just equal to hp here. Right? Okay. So therefore, like this is equal to maximum px hy minus hp, right? So you see, like this is a constant, right? It does not depend on the distribution x anymore.
So where
Yeah.
I can get the HP in there?
Here or like
Yeah, here and there.
hy given x equal to 1 is equal to hp. Do you agree with that?
Why?
Because when x equal to 1, let's say y will have distribution like is equal to 1 with probability 1 minus p,
That's right.
and 0 with probability p.
That's right.
So then the entropy of hy given x equal to 1 will be just minus p log p minus 1 minus p log 1 minus p. And by the way, this is a shorthand notation. People will just call it HP. Yeah.
Yes, that's right.
Yes. So therefore, like hy given x equal to 1 is just HP, right? And similarly, when x equal to 0, again, like you have y equal to 1 and 0 with the probability just flip, but it's still p and 1 minus p, right?
Yes.
And so therefore, like hy given x equal to 0 is still equal to HP.
Equal to 0 is equal to HP.
Yeah.
Yes.
It's still equal to this p minus p log p minus 1 minus p minus p log 1 minus p. So and because hy given this big x here, it's just a weighted sum of hy given x equal to 0 and hy given x equal to 1, right? Both cases equal to hp, so therefore like hy given big x is still hp, right?
Oh yeah.
Yeah. So
Both of them given x HP. Both of them.
both of them, yeah, both of this hy given x equal to 0 and hy given x equal to 1 is equal to hp. So therefore, if you weigh the sum, then this guy I can put it out, right? So it's this just equal to hp. I can put it out. Then it's like hp multiplied by sum over x 0 and 1 like px, right? And again, like this sum over probability is just equal to 1. Right?
Yes.
So therefore, it's just hp. Yes. So because this is hp, then like it's just hy minus hp, right? So the second term does not depend on like the input distribution px. And the first term here, okay, what's the maximum for the first term here, by the way?
HY.
Yeah, what's the maximum of hy?
HY there. P that's 1.
Yes, it will be just 1, right? Hy, it will be maximized. It will be just equal to 1, and that happens when px is uniform, right? If I have px is like 1 is equal to 0.5. If equal to 0.5 for both like x equal to 1 and 0, then the distribution for y will also be py will also equal to 0.5, right? For both y is equal to 1 and 0. So then in that case, hy is just equal to 1. So and so therefore, like this maximized one is equal to 1. The capacity is equal to 1 minus hp. And also you see that when we are going to have the maximum capacity is when px here is uniform. If px is uniform, So we want X to be, the input distribution to be uniform, then we can ensure that we reach the capacity. And then basically it's a pretty simple expression where you have the channel capacity is more or less like your P is 0.5 somewhere here. It would be something like let's see how to draw that. I think P.
So when P is 0, that will be.
Yeah, something like that. I think it's something like that. So if P is 0, then you have maximum capacity equal to 1.
P
Then you
is
just
1 also maximum.
Yes, if P is equal to 1, also maximum.
Yeah, that's
Yeah.
parabolic.
Yeah. Okay, it's a silly question though. P equal to 1, isn't that like loss of error? Like,
Is equal to 1.
yeah.
Loss of error. Yes, that's loss of error. P is error. So it means that when P is 1, yes,
Then why the capacity is also maximum?
Yeah, that's strange. Yeah, because
Yeah.
loss of error.
No, okay, yeah, that seems to be strange at the beginning. So, but be careful, like when you say P, what is P is defined, P is like the crossover probability, right? When P is equal to 1, it's saying that every time I send 1, I got a 0. Then you can simply flip the answer and it will always get correct, right? Isn't that? Like, it's just like you always like flip your input, essentially, for the output. But if your error probability is equal to 1, it's the same as you have no error, because then at the decoder, what you can do is simply flip back. It's like completely deterministic, right? Then you know what you whenever you receive 1, you know the original input is actually 0, right?
Yeah, that's right.
Yeah, so therefore, like it's basically the same as no error at all. Yeah.
Just flip.
Yeah.
from
But on
1
the
to
other
0.
yes, but on the other hand, if like you have like 50% shift, then the mutual information is 0. It's like there's no. It's essentially your output is totally unrelated to the input, because like no matter you are sending 1 or sending 0, you always get something like it's 1 and 0. It's like independent of what you are sending. I mean, what your original input to the channel. Then therefore, like it's natural to expect that the capacity is equal to 0. I mean, oops, make a mess. I mean, like there's no way you can what's that? Extract any information from the output regarding to the input. So this is for the binary symmetric channel. So
So 50% is always we cannot get any information.
yes, that's the worst case you can have. You essentially your output is actually does not depend on the input at all. It's independent of the input. So since it's independent of the input, there's no way that you can send out any information, like, and still retrieve it.
Any channel like that? Yeah, any channel like that?
No, it's not. Actually, you have this binary symmetric channel when your P is equal to 0.5, then yeah, you will have channel like that, but it's just completely useless and yeah.
In the practice, there is
No. if in practice it's like this, it's like, I guess it's just So okay, let's look for an go for another example. So let's look at a Gaussian channel maybe. See if maybe I will start a new page again. Let's see. So consider a Gaussian channel. So in this case, I have x going through a channel. So x is continuous. So I have y going out, and basically y is just equal to x at some additive Gaussian noise. So actually, sometimes it's called additive Gaussian or the Gaussian noise channel or whatever. So C here will be a Gaussian. So like with zero mean, let's say, with some variance sigma square, let's say. And by the way, like first thing first, does it matter if like this is not zero mean? Like why if like C is not zero mean? For example, have a mean 1. Does it affect anything?
No.
Yes, that's nice. Yeah. So yeah, remember that it won't affect anything if things is not because at the output. Then for example, like if you know ahead that the noise have a mean 1, then you can subtract it back, right? At the output, just you just subtract it back. So therefore, like, it's okay. Just assume everything is zero mean here. I mean the noise is zero mean here. So then the capacity again is just equal to maximize the px. And again, in this case, you know this is a continuous channel, right? We mentioned that okay, the theorem applies to both discrete and continuous channel. And then I can write this as y minus h y given x. Now let's leave this alone for the moment, like in the previous example. So let's see for the second term here. I can write the second term as h given hx plus c given x. Now I like to argue that this guy is equal to hc given x. Do you agree with me?
So what?
I mean, I would like to argue that like hx plus c given x is equal to hz given x. Do you agree with that?
Z given x. Oh, that is because x same. So we can rewrite that x.
Yes, actually, this is like kind of general. Like we can also write something like hx, for example, like h fx plus c given x will be just equal to hz given x. So because if you given x already, you know what is fx, right?
Yeah.
Then you can just subtract it back, right?
Mm-hmm.
So therefore, like these two things will be just the same. So anyway, so therefore, like it's equal to that, and then I can further argue that let's see. This is equal to hc because that's simply because we have the setup of the channel. The noise is kind of independent of the input. It kind of makes sense, right? You think of like okay, you have the channel that.
So what is actually z?
Oh, z is the noise. This is the noise.
Oh, that's noise. Okay.
Yeah. So the noise should not depend on the original input, right?
Yeah.
Usually speaking. So therefore, like this will be just equal to that.
Uncorrelated. Independent.
Yes. The noise should be independent of the input. That's typically how people will assume. Will happen. And So let's see. Now, and C is an additive Gaussian noise, right? So therefore, like, we know the entropy of this one is 1/2 log 2 pi e sigma square, right? And
Yeah, that's right.
yeah, so therefore we basically have an expression now is like maximum px hy minus 1/2 log 2 pi e sigma square. I think we talked about a result in the past is that like for the fixed variance, oh, okay, actually I missed something here.
How to calculate
yeah.
hy in there?
Hy here.
Yeah.
Here, yes.
How to
It's
calculate?
still open. Like, I haven't finished yet. Yes.
Oh, yeah.
Oh, actually, I missed out something here in this setup of this problem. I forgot. So I also need to give some constraint on x, right? Because if I just allow to maximize for any px here, so this is a continuous channel. I can make the power of this input as large as we want if we can. Then the capacity will essentially be unbounded. For example, you think of a Gaussian channel here, and you have some additive noise there. If I don't have a control of my input of the input power, I can just arbitrarily increase the. I mean, no matter how large the power applied to that, right? And then I can just arbitrarily increase the zero to noise ratio. Then of course the capacity will increase.
Yeah.
So actually I forgot. Like I should have a constraint that like the variance of x is less than sigma x squared, let's say. So we fix the power. This essentially is the power of the input is a
Yeah, that's right.
not the sigma x squared.
We have limit.
Yeah, we have yes, we're supposed to have limit for the yeah. And now, so what can we if we fix the, let's say like of course like we want to use as many power as possible, then we want to have like, or like let's say the limit is p here, we want to just set sigma x squared equal to p here, right? To use as much power as possible. That's the constraint power. But let's say sigma x squared is equal to p, then what is sigma y squared? Given that like y is equal to x plus c here.
Oh yeah, that's sigma y is sigma x square plus sigma.
Yeah,
That's
sigma square, something like that.
Square,
Yeah,
yeah.
yes. So because they are independent, I assume to be independent, so we have this. So then the question is like, given that sigma y squared is equal to that, remember that we have a result we described earlier on, the maximum entropy for a continuous random variable for a fixed variance, given a fixed variance, will have a Gaussian distribution, right? And therefore, like the maximum hy will be simply 1/2 log 2 pi e sigma x squared plus p something or sigma yeah
sigma x
square plus sigma square, something like that, right? Minus this guy here, minus 1/2 log 2 pi e sigma square. So therefore we got 1/2 log sigma x square plus sigma square over sigma square, something like that. And this is basically equal to 1/2 log 1 plus sigma x squared over sigma square. And this is basically just a cell to noise ratio.
I think this let that
Mm.
you can cancel it. That's right. That's right.
You what?
This one is cancelled with this one. No.
2 pi e? 2 pi e got cancelled.
Oh, this also this one 2 pi e.
Yeah, 2 pi e got cancelled, yes. Wait, there's no 2 pi e here, so that got cancelled, right? 1/2. It's like equal to this over this guy, right?
Yeah,
over this guy.
We'll cancel this directly. That's right.
No, it's sigma x. I have therefore sigma x squared plus sigma square over sigma square, right?
Oh yeah, that's right. Because that is
Yeah.
plus. The operation is.
Yes, there's a plus, yes.
Okay.
So yeah, so therefore like we got this is the expression for the
And that's SNR.
yes, for the each channel used for Gaussian additive Gaussian noise channel, that the capacity is simply equal to this one. And I think like for
That's channel. Channel theorem. That's come from there.
but yeah, everything comes from channel, you can say. Yeah. So
Where's the bandwidth?
no, that's what I'm saying. Like this is a Gaussian channel. This is a kind of, the setup here is assume like you have a Gaussian channel, additive Gaussian noise for applying to each input of a channel, right? So it's something different from that's actually, I should just say like a different expression that sometimes you see like in communication textbook. They didn't even talk about this, but they probably talk about the next one that we are going to talk about is the additive wide Gaussian channel, Gaussian noise channel, the AWGN channel. And we have some kind of bandwidth W, let's say. That's what I think you're looking for.
Yeah.
And then let's say you have a power spectrum of N naught, or like if you have two bands, two side band N naught over 2, stuff like that. Then
so we have two bands.
yes.
Divided by 2.
And then like the what we think we can use what we just discussed earlier to find the capacity of such AWGN channel. So first of all, like think of the Shannon or Nyquist sampling theorem. So we have the Nyquist sampling theorem, So basically saying that okay, if we have a sampling rate or like if we have a sampling let's see, how do we say that? I'm thinking how to say it. Like every time I struggle a little bit about this part. So we think what's the Nyquist sampling theorem? Maybe I'll go back. Do you remember like what's that? Like basically we're saying that like if you have like some we have some signal, right? If some band emitted bandwidth like W, something like that. And the number of samples that we need to represent this signal will be
twice of the bandwidth.
Yeah, will be twice of the bandwidth, right?
Yeah, should be technically sampling.
So now think of this in a reverse way. So if I give you a bandwidth W, that is essentially saying that like you have like 2W degree of freedom, right?
Yes. The minimum, that is the minimum for sampling.
Yes, we have 2W degree of freedoms. Then in the sense that you can think of this 2W degree of freedom is like 2W parallel Gaussian channel that that kind of Gaussian channel like this one here. So therefore, like the capacity, the total capacity will be simply T2W times 1/2 log 1 plus SNR, right? Now, but let's think of like what is SNR will be equal to,
Yeah, because that's sampling.
yes,
Because it's a 1/2W times that.
so and let's see.
That's correct.
Yes, yes. In terms of SNR, like when we have bandwidth W, and also when have the what's that, like the spectral density, the power spectral density of the noise is like N0/2. Then the noise power is actually N0 times W, right? Maybe there's about half there, but I believe the noise is correct. So the power of the noise will be N0/W, and the power of the signal is simply P. So therefore, like this CO2 noise ratio, I can just write it as P over N0W. And so therefore, like the whole thing will be like W after cancelling some of this 1/2 here will be like P over N0W. So that's the equation that's often appear in this communication textbook, right? They will just give it out, but there's no explanation why they got it.
Yeah, that's right.
Yeah, but that's basically the capacity of the AWGN channel. Yeah. So
So M times the W, because that is we have to bend to baseband.
yes. I always got confused with this whether yeah, but it's okay. Like yeah, I believe it's correct. Like either you will miss out like 1/2 or like 2 or something like, but that depends on how you define this thing, right? This two-sided band and so on. That honestly, it's quite complicated. I think it's not very interesting also. So, but yeah, I believe this expression is correct though. Yes. And so that's it for 2 examples. Now I want to go into the proof of why we have how we get this theorem. Basically the capacity of the channel is this one. And so okay, let's start a new page again. So there will be like two parts for the proof. The first is we want to show that as long as the weight is less than the capacity, again it's given by maximums of Px Ixy, then we can ensure that that you can find this is a forward argument. I can find a channel code such that weight is less than C and Miss error free, right? Something like. And then you can always have a backward. The backward will be saying that if the capacity if the weight is bigger than the capacity, then we are doomed to have error. Basically, there is error in the transmission. Yeah.
That's right.
So we look for the forward path, forward put first, the forward part first. first of all, like we have the weight. Let's say we have the weight is a little less than the capacity. So assume that like we are going again like we use the channel n times. So if you remember the picture that we have early on, basically we are going to have a message coming in, the encoder for some message, then we encode the message into a sequence of code word, like let's say have length n. So I have a length n sequence. I'm going through this channel, get y1 to yn and so on, and then we decode that to get m hat again. Now, so since the weight is r, it means that like there will be like 2 to the n r so many messages. So therefore like the set of messages, I mean write it m will take value like 1, 2 and so on, 2 to n r of them. They're the messages. And I will assume a binary channel here just for simplicity. It will map into, essentially map to a sequence of like 0 and 1 of length n sequences, and going to pass through this channel.
Actually, for the dash messages, what's the physical meanings in here? Check. 1, 2. This is one message.
That's not some. Okay, this is just a label. So for example, like this can be
index, just index.
Yeah, this is just index. So we say saying something like any kind of information that, for example, you think of like a multiple choice, like A, B, C, D, E, or you want to send this information to the other side. Yeah, you can send yeah, that can be, yeah.
And how much the length of that for one that is, how much this one?
N?
This, yeah, the length.
You mean the N
one.
here or like?
The length of 1 and 2, 3 and how many the length? Okay. For that, for every message, how many the length?
Oh, here we just okay. Let's assume we send one message at a time here. Just consider now sending one message now.
Just A.
Just one message now. But the A can be all of like, for example, 26 alphabets, right? We're sending A now, right? But maybe next time we send B or something like that. Yeah. But just let's say.
We can send A, B, C, 1.
Yeah, you can put them together, but then like you can make A, B, C together as a one alphabet, right? Then you then in that case you are 26 times 3 different combinations, right?
Yeah, that's right.
And then this will be your kind of messages, and then you code them into this sequence, right?
Oh.
So you yeah. This is a very kind of general form here. The only assumption is that we are we're basically assuming that n can be large. We want to make n pretty big. So it's actually we are indeed like grouping many information together as one label m, and then like for that big label, we are going to code into sequences, a long sequence, and then send through the channel.
Okay.
Yes. They will want to make sure that like each time we recover, like we have very low probability, or like the probability of errors should approach 0.
But in this case, one symbol, one message.
One symbol, one message.
Yes.
For m here,
Yeah, and then.
we are only considering sending one symbol now. Yes.
Okay.
Because one symbol is enough. Because this can be itself, m is like some random variable you can think of. So we just need to study like what's the probability that m is not equal to m hat. We want to show that this is like very small, go to 0. So basically, how Shannon proved that is using a random coding argument. it doesn't. It's not a constructive kind of approach. Like, given like the whole proof, it's not clear how you are able to implement that. But logically, it can show that okay, indeed, as long as R is less than the capacity, then you can potentially send information like error-free. And so the random coding argument will be like, I'm just generating a codebook that is kind of randomized codebook, and first let's assume that like px star is the distribution that maximizes ixy, or in other words, like px star is actually the distribution you want, like the input distribution you want that will achieve the capacity. And then like we'll generate codebook according to this distribution px star. So how to generate this codebook will be very simple, right? So we think of like now we have a discrete memoryless source, like we always study. We have a discrete memoryless source, and this discrete memoryless source is coming from this p star x here. And then the code word of this codebook will be simply drawing from this source here. So for example, like I will essentially just basically draw 2 to the nr kind of like sequences from this codebook, and each of them are of course a length n here. So maybe I have C1, the first code word here is like x1 1 up to like x and 1, something like that. So I'm basically just drawing from this source here. This is a code word, and I draw it like 2 to nr times. So because I have like 2 to nr different messages, right? I'm sorry, I said like 2 to nr different messages. I mean, yeah, I see why you're confused. Maybe my wording has problem. I mean, like the message has 2 to nr different outcomes, right? Different possible messages,
yes,
so to choose from, and each of them like can have a different code word, should have a different code word.
So that is the code word. It's a unique.
Oh, actually, we didn't even care about it's unique or not. This code word is simply constructed from drawing from this distribution. So we draw this like 2 to nr times. Maybe there will be like overlap of the code word. Maybe some of them is the same. We don't even care. Well, so we just assume okay. We start drawing the code word. Say yeah.
Overlap in here something like this is x1. This also there is x1. Something like that.
Yes, even possible. Like there's a very small possibility that you may even have like 2 exactly identical code words. But we can show that this probability is really, really small. Therefore, it won't affect us.
Okay.
So, but the idea to build the code word and the code book is extremely simple. You simply have this discrete memoryless source, and the distribution of the source is just the distribution that maximizes ixy, or the one that achieves the capacity. And then you just draw this sequences like multiple times, basically, more accurately 2 to nr times. Yeah.
And what is the definition of code book in here?
Code book will be all these code words, a compilation of all these code words. Yes, this will be the code book. And so essentially, the encoding will be very simple, right? Encoding will be like if I receive a kind of like actual message, say M here, then I will just send out CM. And this CM is just constructed right for here in the code book. And then this CM will then pass through this channel. Yes. Yeah. So therefore, like very, very simple encoding. Now, in terms of decoding, Of course, because the channels has error, so decoding you won't expect to get exactly the same as the same cm here, but we should receive a sequence y here, right? A yn here at the decoder. Now, what we're going to do is you simply look through the codebook and see if we can find a cm hat here in the codebook that is jointly typical with the sequence.
Has maximum correlation.
Actually, it isn't even necessary. Remember that how we define the jointly typical sequences, right? We define jointly typical sequence would be simply saying that like I have the probability of xy will be within the range, or like will be approximately equal to 2 to n hxy. Yeah, and also px is approximately 2 to n hx and so on to ny2. So here we just say, okay, in the codebook here, we have so many different code words here. You see that which code words will be jointly typical with yn. There may be more than one, then there will be error. Or in some cases, there will be only one, then we'll just decode. I'm saying that, okay, we find the m hat here, this c m hat here is actually jointly typical with yn, the output of the channel. So therefore, we say like the message is m hat. Very simple, right? So in this case, a message, decode message.
So to decode message, just looking for that requirement.
Yes, just look at one requirement here. So, and there's chance failure if only one m hat satisfy the above. Otherwise, failure. So we will have failure cases if you have more than one.
So we will have a lot of error then.
Yeah, but we'll show that actually we won't have that many. Yes. If we have more than one, there will be errors. If we cannot find this jointly typical, we cannot find m hat, there will be error as well. So the whole point is we want to show that on average the error is very small.
Very small.
Yeah. So therefore, as long as your r is less than c, as long as n is going to infinity, then the error is very small. So then this simple random coding random codebook argument is sufficient.
R less than c, and then
n should be large. R less than c, and n should be large. N should approach infinity. Yeah.
So the channel coding here is to improve the correcting message we get in the receiver. That's right.
Yeah, you can say so. Because the channel have noise, right?
Yeah.
If you just simply send without coding, then there will be error. So the channel, yes.
Depend to the SNR.
Yeah. Yes. And the channel coding procedure is essentially introducing redundancy to your message, right? So because now you have redundancy at the decoder, you can take advantage of this redundancy to try to remove those errors to recover the original message.
That's right.
So now if you are clear if this setup, then we can kind of try to analyze the performance here. So as I already kind of jumped ahead earlier, it turns out the error probability is actually pretty small. That's why this is sufficient. This scheme is sufficient to show that the forward part of the channel coding theorem. So let's look at all kind of error cases when we will have failure. So first case will be for example, if let me call it P1, the first error event is probability. The probability of the first error event is that I have CM and Y are not jointly typical with, are not jointly typical. Well, I mean, if this happened, then definitely will be error, right? So you send out M. It turns out that CM is actually is not jointly typical with the Y. Then I decode we won't decode M has as M, but we'll decode it as something else. So, but this is okay. This is exactly the packing argument, right? Oh wait. They said this is not the packing one. Let's see. This is okay because think of what we have here. Okay, yeah. What we have here is we have CM is coming out of this PX source here. This is a CM here. And then this one, actually maybe I better redraw this. You have PX or PX star. They conjure a CM here. And then this one also go for a PY given X, right? And to get a YN, right? And then this whole thing, if you look at CM and YN, it's essentially just pulling out from a joint source here, right? And the joint source is actually a distribution PYX, something like PYX star or whatever PYX. Maybe I just write PYX. And yes.
So what's the PX star? What is the PX star there? What's down there?
Yeah, this we mentioned earlier. X star is actually is the distribution that reach the capacity. But I guess I would just for later on because we want to pick that one such that it will reach the capacity IXY, right? But actually if we pick some other things, we'll just still reach IXY, but it won't reach the capacity C, right? So therefore we want to pick the distribution X that is reaching the capacity. But for simplicity, I guess I would just use PX instead of PX star because we can always switch back to PX because PX star later on because the same arguments simply apply. So we can just
to maximize on the capacity.
Yeah. PX star is just the one that actually maximizes the optimization problem in the capacity. That will reach the capacity. So then, but if you look at again where we got CM and then YN, CM is basically just drawing from a distribution PX, right? And then this CM then will fit into a channel with distribution PY given X. So therefore, YN, the output of YN is essentially I mean, CM and Y together is essentially a coming from a joint distribution PXY, right? Let me write PXY maybe.
joint distribution
Pxy.
Cn and Yn.
C, yes, but Cm is it's drawing from a distribution of x, so
how to write the Cn is joint distribution in Yx. Cm is actually just come from P star, Px star.
yes, it's true, but you yeah, okay, that's true, but you think of like when you say Pxy, you can also write it as Px and then Py given x, right?
Yes, that's right.
So you have this, of course, it's just drawing from Px here, but then the important point is like, how about your y? Y is like, it's getting out like each time, like first you have x, then going through this conditional distribution to get y, right? So therefore, like if you look at that x and y as a pair, it's essentially the same as like coming from a Pxy, right?
Yeah, that's right.
So since this whole thing is like coming from a Pxy, then just by the typical sequence argument, like everything coming from a joint distribution should be jointly typical. So therefore, like the probability that like this guy to be not jointly typical will be very small. So this will be negligible. So this should go to 0 as n goes to infinity.
Oh, yeah.
Yes. And then like the second one, second error can be like, let's say if there exists some m pi is not equal to 1, or sorry, not m.
If
Yes.
Py given x is too much 0.5, so that will be high error.
Oh, yeah, but then in that case, like,
It's like that, the above condition will be reached.
but yes, it's true, but then this one is still jointly typical, but it's kind of trivial. It's like the case that, or I should say like, in that case, it will still be something reaching the capacity, but the capacity will be equal to 0, right?
Yeah,
Yeah.
that's right. C into 0. All of the error, the error rate is 0.5. So the capacity to 0.
Yes. Yes.
So we don't have Pxy then.
No, okay. But still have like, okay, it is actually okay.
Because in here is 0. If this is 0.
No, okay, wait. This is not 0. You cannot have this one suddenly become 0.
I mean the capacity.
Oh, okay. The capacity is equal to 0. It will just wait a sec. Like what we're talking about really?
Parabolic shape, and there is capacity 0.
EYP let's see. This is let's don't go that far first. Let's see like what we are just trying to claim. We're just trying to claim that like for the sequences to be not jointly typical to be very small, right? So because like for the setup like that, So when you have like this, let's say this is independent, right? If like you say like the capacity here is like 0, then in the sense like y and x will be independent, right? So you just go back like you actually have it doesn't actually change anything. You have like still have the same picture here, but you have a dummy kind of channel here. This is like
or something like
disconnected.
Yeah, disconnected. Really disconnected.
Then you yes, and then you will have like px
and something
py,
like yeah, py.
and then like you have something like this, something like.
Yeah.
But then like remember like how do we define Johnny typical? The definition of Johnny typical depends on the original distribution. So in that case, like actually quite the opposite. Everything's like coming out of these two will be like Johnny typical because like then actually may not, but as long as they're independent will be Johnny typical, because like then in that case, even though like you have a picture like this way, but then in this case this is actually considered to be Johnny typical because in that case you expect this pxy is actually sequences that are independent will be considered as Johnny typical.
But in the channel there's a cutoff, therefore py given x is something like don't have.
Okay. Yeah. Again, like I guess I mentioned that, but maybe I didn't emphasize that enough. Is like if you remember, at the beginning of the class, we say that like we have like two independent like x and y, px and py, and we say like under what situation like these two guys will be Johnny typical. We say that like the probability like for these two sequences independently drawn from this px and py to be Johnny typical will be like probability 2 to the n ixy, something like that, like close to this guy, right? Yeah. And but be very careful, like when you have the probability of like Johnny typical actually depends on the joint distribution pxy themselves. So therefore depend on this ixy itself here. So if at the beginning you have like your joint distribution itself is like independent of one another, like pxy is equal to pxpy, then actually any sequence drawn here will be Johnny typical as well. So Johnny typical, be very careful, it's not equal to, this is something like similar to correlation or like something like that, they will be correlated or something like that. But there's a fine pin of the definition is.
But how is something like independent there is correlation?
But that's what I'm saying. The definition of Johnny typical, there's although sometimes you kind of like seems like okay when they are Johnny typical they are correlated or something, but it's not. The definition, look at the fine print there. The definition is just saying that like if something is Johnny typical, they just behave like they are pulling out from a joint distribution. Yes. Behave like drawing from a joint distribution is a very vague description because you didn't describe like what is your joint distribution, right? You can have the joint distribution to be independent to start with, right? Then in that case, even though you are Johnny typical, it doesn't mean that they are correlated. So it depends on like what is the joint distribution to start with. So here, therefore, like in this example here, you say, okay, how about these are actually independent? It doesn't matter. In that case, they are still Johnny typical, but they are not correlated to one another. And we are only studying here is like what's the probability that CM and Y are not Johnny typical, right?
Even that is not independent each other, it's limited because we don't have any already. I mean that we don't have any connection then.
If they don't have, for example, if this kind of breakdown, like this is a.
Therefore, there is no really there is no correct. There is no independent. There is this really independent in this one. So, yeah. So all of the requirement for joint typical format is joint distribution is gone or not?
Oh, okay. Again, let me repeat again. The definition of joint typicality. Maybe I just write it on a new page somewhere. So we say like xn and yn are jointly typical. So essentially it's just saying that like, okay, in a kind of like layman sentence would be like xn is jointly, okay, they are jointly typical. Is equivalently saying that like xn and yn pull from the joint distribution pxy.
Yeah, that's right.
But that's be very careful. This is essentially the core of the definition, right? But it didn't specify pxy. What's pxy? Right? It didn't specify. It gives you the freedom. Like there's a freedom here. What is pxy is not specified here. So if you pick pxy is equal to px times py, or saying that like x and y are independent, then you say something like sequence xm and yn are jointly typical, doesn't mean that like xm and yn are correlated, right? You see my point here? I mean like
the last one.
If you pick xy, pxy as like pxpy,
Yes.
then x will be independent of y, right?
Yeah, that's right.
Now you say like xn and yn pulling from the joint distribution pxy. That joint distribution is actually an independent distribution, right? Then it doesn't. Then in that case, like xm and yn are not correlated, really, right?
Yes, that's right.
So what it means is that be very careful. When you say two sequences are joint typical, it doesn't always mean that like xm and yn are correlated. It's just saying that like they are coming from a joint distribution. But you didn't specify the joint distribution. What is the joint distribution yet? The joint distribution can be highly correlated, or they can be independent completely.
Yeah.
So if for the latter case, then they are coming from that joint distribution, but they are independent.
Yeah.
Yes.
So it means that even that independent is no problem that can be at the last.
Yes, it depends on your,
Yeah.
it doesn't affect your argument here, right?
Doesn't affect that.
Yeah.
Even that is independent.
No, it doesn't affect it. So if you have a very poor channel, this is essentially making it independent. It doesn't affect it. Like your probability here is still like very small or something like that. But then like in that case, of course, your weight is actually super small as well. I don't know what's the consequence for that. Of course, if it's a completely independent, some things may break down because in that case your weight is actually equal to 0. So most likely there will be something to break down. But as long as it's not completely independent, then yeah, everything is okay. Like I mean, in this proof is okay. But for this argument here, still like it doesn't matter whether it's independent or not. Apparently, it doesn't affect anything.
Doesn't affect anything. Even
Yeah.
that is really independent. It's really independent.
Yeah, it doesn't affect because in that case it's just your pxy will be actually px times py. Yeah, and you still have like anything drawing from cn and y to be not jointly typical is still like have very low probability. Because in that case, how you define something to be jointly typical is essentially like they are actually independent.
If something like that, it is something like if I can make it that this is random. No need this one. Just give us some box in here. and randomly go to here, and it can catch this one too. So that's something like because you can put this to anywhere, just go from somewhere. And
No, it's not. I mean, like here we still have the py given x, but you are just saying that if like this py given x is essentially something like, for example, like this py given x turns out to be py given x is just equal to py
Yes.
for some py, then essentially like this is like actually independent, right?
Yes, that's right.
So, but what I'm saying that it okay. First of all, I guess I don't quite get what you want to point out here, like when you're on the screen, but even your py given x is equal to py here, so that it just means that your joint distribution of pxy is equal to px times py.
Yes, that's right.
And then your definition of like things to be jointly typical will just be the same as I saying like two sequences to be independent. Then you have one sequence coming in through the channel that is going out, that sequence to be completely independent with the original. Then it's actually by definition is still jointly typical. So therefore, like the probability for them to be not jointly typical is still going to be 0 as n goes to infinity. So let's see. I guess I'll stop here because there would be like a lot more to say to finish this proof here. I may repeat a little bit again next time, and then yeah, we'll just continue next time then. Yeah. So I guess I will just stop here.